Hello. We're going to do a very basic example of application of Kirchhoff's rules to a simple circuit here, as simple as we can get, using the loop rule. I figure that the junction of the current rule is actually a pretty simple and straightforward one, so this is where students a lot usually get hung up on and get stuck. So I'm going to go ahead and explain this one, and I'm going to go to more complicated examples in other videos. Okay? So let's check this out. Here we have a source of EMF or electromotive force that drives the current, that adds the potential difference, that adds the potential energy to push the electrons across the circuit, and it goes through a resistor. Okay, so as you can see here, with the direction of the current, that is given to us, it is actually going in a clockwise direction. Okay. And recall that for the loop rule, the basic formula that represents that rule is based on the law of conservation of energy, or that the sum of all the potential difference across it has to equal to 0. Okay? Or you can rewrite that as the sum of all the rise in potentials should equal the sum of all the potential drops. Now in this case, we actually only have one component that gives result in a rise, and this, the resistor, result in a voltage drop. Okay, so we can use either one of these. I can show both as a matter of fact. Just do a dividing line right there. And so if I use the first one, it will look like this. Just move that up a little bit. The sum of all the potentials, and if I go here, it's actually by going that direction, and it goes, take note that it goes along with the direction of the current, so the source of that EMF is going to be positive. Okay, now the current here, we're actually traversing along with the current, okay, because our direction is going clockwise, so we're actually going along with that. Actually didn't show up. It's black. So we're going along with that, but it results in a drop. So that becomes minus, and the voltage drop is basically described by Ohm's law. So in this case, it's going to be small I, capital R. And all of that, according to our equation, has to equal to 0. Okay, and I'm just going to get this part of the formula, so I basically don't even need that. You know, I use that to set up, and from here I can move this part to the other side by just adding IR, add R, and I get that so that cancels out, E equal to IR, and pretty much that's an equation that we could possibly use depending on what this formula problem is given to us. Okay, and I should get the same result if I use that formula. So there's one rise, so the rise equals the drop, so I'm going to say rise, drop. There's one potential rise, and then the drop is simply IR, and it's not negative this time because it's already on the other side. Okay? That one was just pretty much one step, but I kind of like this first one because it's a bit more intuitive, at least to me. Because say either way should give you a way to analyze a very simple circuit like this. Now, even though it's very simple, it actually doesn't do much. Okay, it gets more interesting when you add other components in the mix. Okay, so that's a basic example of how you use Kirchhoff's loop rule. Enjoy.